In this video, we will be going through examples of how to draw Lewis structures for some of the more challenging types of structures. The first one we're going to look at is HCN. So first thing we need to do is determine how many electrons we are going to work with. We have hydrogen, which has 1 valence electron, carbon, which has 4, and nitrogen, which has 5, for a total of 10 valence electrons. Normally we start by taking the leftmost atom, except if it's hydrogen. So in this case, it is hydrogen. So we will put carbon in the middle. So we'll have carbon in the middle, draw out a nitrogen, and add a hydrogen. Bind them all together to the central atom. That took 4 electrons to do. And so we have 6 electrons left. We will put them around our most electronegative atoms on the outside first. 1, 2, 3, 4, 5, 6. For the hydrogen, we do not add any additional electrons to it because hydrogen is capped at 2 electrons, which is satisfied by the chemical bond that it currently has. Looking at our structure here, nitrogen has a filled octet, carbon does not. We're going to write out our formal charge to determine what we need to do. So for our formal charge, that is the number of valence electrons minus non-bonding electrons minus 1/2 of our bonding electrons. For carbon, carbon has 4 valence electrons minus the number of non-bonding electrons is 0 minus 1/2 of the number of bonding electrons, which is 2 from each bond for a total of 4. So carbon has a +2 formal charge. Nitrogen brings with it 5, so it has 5 valence electrons minus non-bonding electrons. It has 6 minus the number 1/2 the number of bonding electrons, 1/2. It has 1 bond, so that is 2 electrons. 1/2 of 2 is 1. So our nitrogen would have a -2 charge. The hydrogen has 1 valence electron. It has 0 non-bonding electrons and 1/2 of 2, or 1, bonding electrons, which gives us a 0. So we have opposite formal charges. We have a +2 for our carbon, a -2 for our nitrogen. We have opposite formal charges sitting next to each other. So we're going to get rid of those by taking some of our non-bonding electrons from one of the atoms that has a greater negative charge and shifting that on to our atom with a positive charge through forming an additional bond. So we're going to take those 2 electrons, form an additional bond, and in doing so we get rid of these electrons here. We will need to recalculate our formal charge. So for our carbon, we have essentially not changed the number of non-bonding electrons, but we have changed the number of bonding electrons. We now have 1 single bond and 1 double bond, so there are now a total of 6 bonding electrons. 4 minus 0 minus 1/2 of 6, which is 3, gives us a +1 charge. For our nitrogen, we have now 4 non-bonding electrons minus 1/2 of our number of bonding electrons. It has a double bond, so that's 4 bonding electrons. This gives us a total of 5 minus 4 minus 1/2 of 4, which is 2, gives us a -1. So in making these bonds, what we've essentially done is reduced the formal charge on the carbon and increased the formal charge on the nitrogen, bringing them both closer to 0. Looking at our 2 atoms, carbon still doesn't have a filled octet, and we still have opposite formal charges sitting right next to each other. So we can repeat the process, taking now the set of lone pair electrons, forming a new bond, and erasing our old ones. And we will now recalculate our formal charges. For carbon, we still have 0 non-bonding electrons, minus we now have a triple bond. So we have a single bond and a triple bond, which means that we have a total of 8 non-bonding electrons. So 4 minus 0 minus 1/2 of 8, which is 4, gives us a 0 formal charge. For our nitrogen, we have 5 minus nitrogen now only has 2 non-bonding electrons, minus 1/2, it has a triple bond, which is 6 electrons. So 5 minus 2 minus 1/2 of 6 is a 0. Looking at our next example, CO2, we have carbon, which has 4 lone pair electrons, oxygen, each of which has 6, and there are 2 of them. Add them all together, and we get a total of 16 electrons to work with. We're going to put our carbon in the middle, bond it to our 2 oxygens. It takes up 4 electrons total, so we have a total of 12 left. Put them around our outermost atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now we're going to work out our formal charge for carbon dioxide. So that's the number of valence electrons that the atom brings with it, minus non-bonding electrons, minus 1/2 of our bonding electrons. For our carbon, carbon has 4 valence electrons. Right now there are no non-bonding electrons, and 1/2 are bonding electrons. We have 2 bonds for a total of 4 electrons. 1/2 times 4, so it's 4 minus 0 minus 1/2 of 4, which would be a plus 2. Our oxygen, each bring with them 6. Each of the oxygen has 6 non-bonding electrons, and each has a single bond. So 1/2 of 2 is 1. Doing that gives us a -1 on each one of our oxygens. Okay, so what we can do is to get rid of the opposite formal charges. First thing we need to do is look at the atom with a plus charge. Can it accept more electrons? Carbon is in the second row, so it is hard capped at 8, but it currently only has 4 electrons around it in the form of the 2 bonds. So we can take 2 electrons here, and as we saw before, when we do this, it will reduce the formal charge on the -1 to be 1 less than what it was before, or closer to 0, so this would become a 0. For our carbon, it will cause it to go down to be closer to 0. So our carbon would then become a +1 formal charge. So we would end up having a -1 formal charge on the oxygen on the left and a -1 formal charge on the carbon when we form our double bond. So let's try that out. So in doing this, we use up these 2 electrons. We need to recalculate the formal charge on the ones that we just did. So for our carbon, 4 minus, there are still no non-bonding electrons. Now it has a double bond as well as a single bond, so that's a total of 6. So we're now down to +1. For the oxygen on the left, that is the single bound one, so we're going to label one oxygen with single bond and create a new entry for the double bonded one. So that has 6 minus the one on the right has 4 non-bonding electrons. It has 1/2 of the bonding electrons. It now has 4 through the double bonds. So this gives it a total of 6 minus 4 minus 2 is 0. So we can now look to see if we need to make an additional bond to that carbon, because we still have opposite formal charges sitting right next to each other. The central carbon currently has 6. It can hold up to 8, so it can accept an additional 2 electrons to make an additional bond. So we make our bond here, erase the electrons, and then we are going to need to recalculate our formal charge. When we do this, we make a double bonded oxygen the same as we had before. So essentially, we're getting rid of any single bonded oxygen. Both of our double bonded oxygens are the same, so they will both have a 0 charge. Our carbon, if we want to recalculate it, would be 4 minus 0 non-bonding electrons minus 1/2. We now have 2 sets of double bonds, which are 4 electrons each for a total of 8. 1/2 of 8 is 4, so 4 minus 0 minus 4 is 0. So our carbon now has a 0 formal charge. The oxygen now has a 0 formal charge. And so everything has a nice 0 formal charge. Our next example, Cn-, is very similar to our first one. The only difference is now we have a charge. So we have a carbon, which has 4 valence electrons. We have a nitrogen, which has 5. This time we don't have a hydrogen, but we have a charge. The charge is negative, which means we have an extra electron, so we'll add an electron to our total, giving us a total of 10, just like we had before. So we'll have carbon bonded to the nitrogen. And as we go through this, what we'll find is we get the exact same thing that we had before. We got 10 electrons. We just bonded 2. So we have a total of 8 left over. We will put those around our nitrogen. 1, 2, 3, 4, 5, 6. That's used up 6. We have 2 left over. And so we are going to put those on our carbon. So 8 minus 8 gives us 2, minus 2 gives us 0 electrons left over. Okay, just as we had before, working out the formal charge. Which is number of valence electrons minus non-bonding electrons minus 1/2 of our bonding electrons. For carbon, there are 4 valence electrons. We have 2 sets of non-bonding electrons minus 1/2. Currently we have 1 bond, so that's 2 electrons, which will give us a 4 minus 2 is 2 minus 1/2 of 2 gives us a plus 1 formal charge. On our nitrogen, we have 5 valence electrons minus, there are currently 6 non-bonding electrons, minus 1/2 of the number of bonds, which is 1, so that's 2 electrons, which gives us a 5 minus 6 minus 1/2 of 2, which is 1. So that's essentially 5 minus 6 minus 1, so that's a negative 2 formal charge. Writing this out, our nitrogen has a minus 2, our carbon has a plus 1. And so what we can do is remedy this situation by taking 2 of the electrons from the nitrogen and forming a double bond here. In doing that, we've changed the formal charge on our nitrogen and our carbon. So for carbon, it's 4 valence electrons minus still 2 non-bonding electrons minus, now we have a double bond, so it's 1/2 of 4. So that would now be a 0 formal charge. For the nitrogen, it's 5 minus 4 minus 1/2 of 4, which would give us a minus 1 charge. So we have a minus 1 that's on the nitrogen. This case, the nitrogen is more electronegative, so we might think that we're done there, but our carbon does not have a complete octet. So this is one of those exceptions to the general rules in which we need to form an additional bond so that carbon can get a filled octet. Filling this out, Going back and doing our formal charges, for carbon it's 4 minus non-bonding electrons is 2 minus 1/2 of our bonding electrons, which is 6 through the triple bond. So carbon will have the -1. Nitrogen, 5 minus, it has 2 non-bonding electrons, minus 1/2 of 6. 5 minus 2 minus 1/2 of 6 is 0. So our correct structure for Cn minus would be this here, and the carbon is what would hold the -1 formal charge. We do that so that we can have the filled octet on the carbon. Let's look at a couple more examples. We have the nitrate ion. First thing we need to do is figure out how many electrons we have to work with. The nitrogen brings with it 5 electrons. Each oxygen brings with it 6, and we have 3. And then we have a charge of -1. The way we get a -1 charge is by adding an additional electron. So we will add 1 to our total number of electrons. This gives us a total of 24 electrons to work with. So we're going to put our nitrogen in the middle and then bond it to our oxygen. In doing so, we've used up 6 electrons, so we have 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Minus 18, we have 0 electrons left. Looking at our molecule, each of the oxygens has a filled octet. The nitrogen, however, does not. If we look at our formal charge, that's the number of valence electrons minus our non-bonding electrons minus 1/2 of our bonding electrons. So for our nitrogen, nitrogen has 5 valence electrons minus the number of non-bonding electrons, in this case are 0, minus 1/2 of our bonding electrons, and in this case we have 3 single bonds, so that is a total of 6 bonding electrons. This gives us a total of a +2 formal charge. Each one of our oxygens is the same in what is around it. Each oxygen brings with it 6 valence electrons minus the non-bonding electrons. Each one has 6 non-bonding electrons. And then we subtract off 1/2 of our bonding electrons. Each one of them has a single bond. A single bond is 2 electrons, so 1/2 of 2 would be 1. So 6 minus 1 is -1. So each oxygen has a -1 formal charge, and our nitrogen has a +2. Now what we need to do is form double bonds in order to get rid of our opposite formal charges. If we look, each one of those oxygens is identical, and so we just need to pick one to form our first double bond. So we're going to take this one here, take those 2 electrons, form our double bond right there. In doing so, we've used up these electrons, so we'll erase them. We need to adjust the formal charge on those 2. Recalculate it. And now we have an oxygen with a double bond. So we're going to sublabel the first oxygen as SV for single bond, and then we have ODB for our double bond. It has 6 valence electrons minus, it has 4 non-bonding electrons minus 1/2. It now has a double bond, so 4 bonding electrons. This gives us a total of a 0 formal charge. For our nitrogen, there are 0 non-bonding electrons minus the number of bonding electrons is 1/2. We have 2 single bonds and a double bond. That's a total of 8 electrons. So 5 minus essentially 4 gives us +1 formal charge and a 0 for our oxygen. Okay, so looking at this, we do have opposite formal charges sitting right next to each other, but the problem is that nitrogen has a filled octet and it is in the second row of the periodic table, which means it is hard limited to a total of 8 electrons around it, which it currently has. So our nitrate ion cannot form any additional double bonds. So it will by necessity have to have opposite formal charges sitting right next to each other. But because we selected somewhat at random one of the oxygens to form the double bond, when we could have selected any of the other oxygens, we will have resonance structures. And where those resonance structures are going to differ is the location of that double bond. So we could also draw this as the nitrogen with a double bond to the bottom oxygen, and we could also draw this as a double bond to the leftmost oxygen. Each one of these is a correct Lewis-Dot structure, and we actually need all of them to have the overall correct Lewis-Dot structure. We need to show that the actual structure is a resonant hybrid of these three structures. Because there is an overall negative charge on this molecule, we need to put a negative in the upper right. The next one we're going to look at is Cl O4-, the perchlorate ion. We have chlorine, which has 7, and then we have oxygen, which has 6. There's 4 of those, and then we have a -1 formal charge. Because it's a -1, that means we have an extra electron, so we will be adding 1. This gives us a total of 32 electrons to work with. We're going to put our chlorine in the middle. And in order to free up space, I'm going to erase our resonance structures for the nitrate ion. Okay, so we're going to start by drawing our chlorine in the middle. We have 4 oxygens around it. Okay, in bonding everything together, we used up 8 electrons. So we have a total of 24 left. We will put our electrons around our oxygen: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So looking at the structure, each one of our atoms has a filled octet. So what we're going to do is double check everything by writing out our formal charge. Formal charge would be our number of valence electrons minus our non-bonding electrons minus 1/2 of our bonding electrons. So for a chlorine has 7 valence electrons minus our non-bonding electrons, there are none around it, minus 1/2 of our bonding electrons, 1/2 times, there are 4 bonds to it for a total of 8. So this would be 7 minus 0 minus essentially 4. So that would give us a +3 formal charge on the chlorine. Our oxygen atoms each bring with them 7. They are all the same in terms of what is bound to them. They all have 6 non-bonding electrons minus 1/2 of 2 bonding electrons, giving each one a -1 formal charge. So we do have a lot of opposite formal charges sitting right next to each other. Because chlorine is in the 3rd row of the periodic table, it can actually have an expanded octet. So it can accept having more than 8 electrons around it. It will do so to get rid of opposite formal charges. So that means what we will be doing is forming additional bonds. So we're going to take this oxygen, make a double bond to get rid of the opposite formal charges. And as we've seen before, when we form an additional bond, the thing that had the negative charge increases in number, going closer to 0. And the other one, the one that had the positive charge, decreases in value, also becoming closer to 0. Because we form one bond, the oxygen is now going to go from a -1 to a 0 formal charge, and the chlorine will go from a +3 to a +2 formal charge. You can write out the formal charges to verify this. We still have opposite formal charges, and chlorine can accept more electrons to get rid of those opposite formal charges. So what we'll do is take an additional 2, make another bond, in doing so, that gets rid of these electrons here. It will increase the formal charge on the oxygen to go from -1 to 0, and it will decrease the formal charge on the chlorine, now going from +2 to +1. Okay, we can form an additional bond to get rid of the remaining opposite formal charges. Take these two, form a bond. Our double bonded oxygen here will go from a -1 to a 0 formal charge. And our chlorine will now be a 0 formal charge as well. Let's work those values out to show that the double bonded oxygens do have a formal charge of 0, and now the chlorine has a formal charge of 0 as well. So for our chlorine, we have 7 valence electrons minus the non-bonding electrons are 0. In terms of the bonding electrons, 1/2 of our bonding electrons, we have 3 double bonds for a total of 6, plus an additional single bond for a total of 7 bonds. Each bond has 2 electrons, so that's 14 electrons total. So 7 minus 1/2 of 14 is 0. Our single bonded oxygen is still the same, but we now have an oxygen that has a double bond. The oxygen with a double bond, each one of them has 6 valence electrons minus the non-bonding electrons, each one has 4, minus 1/2 of the number of bonding electrons. Each one of those has a double bond for a total of 4 bonding electrons. So 6 minus 4 minus 1/2 of 4 would be 0. When we were doing this structure, we selected the 3 oxygens that would get the double bond. But we could have selected the oxygen on the bottom to have a double bond. This tells us that we're going to have resonance structures. So drawing them out, what we will do, when I'm doing something like this, I like to move the odd type of bond in a clockwise direction. So we have the single bond pointing down, which is different from the other 3. So I'm going to rotate it around in my structures going clockwise. So we have a resonance structure with chlorine in the middle, and now I'm going to be single bonding the oxygen to the left, double bonding all the others. That's one structure. We have another one. Chlorine in the middle, single bond to the top. And then one last structure, chlorine in the middle, single bond to the right, double bond in the other directions. Square bracket around the whole thing, and there would be a -1 in the upper right. We sort of ran out of space there. Okay, the correct structure for the perchlorate ion is all 4 of these with the double arrow between them to show that they are resonance structures. Each one of these is not fully correct. It's a combination of all 4 structures.